Hello, and welcome to this series of lectures on symmetric computation, which I have prepared together with Gregory Wilsonak. In the course of this series of lectures, we're going to give you an introduction to the study of symmetric computation. Now, the idea is the following. Many natural algorithms working on abstract data structures have certain properties of symmetry. And this symmetry can be both used as an algorithmic technique, but more interestingly, used to show certain impossibility results, that certain kinds of computations are simply impossible within resource bounds under the assumptions of symmetry. So this kind of symmetry arises in many natural ways, and there is a sort of surprising unity in the methods used for proving the impossibility results for these. So in this first lecture, I'm going to give you an introduction to how symmetry arises in computation in several different contexts, and then we will go on to examine the common underlying themes there. So to begin with, let me start with a quote, which I really like. This is due to Aho and Ullman, and it appears in their famous Foundations of Computer Science textbook. They say computer science is the mechanization of abstraction. And I love this quote because it captures very pithily, with two key words, the essence of what a lot of computer science is about. I want to focus on the word abstraction. When you want to solve a problem computationally, the first step is to formulate it as an abstract problem. And that means stripping away irrelevant concrete details. Let me give you an example. I was once supervising a student who had a project in which he had to construct, using a constraint programming language, a railway timetable. And I found that the hardest step was the first step, where in order to know what to program, you had to formulate what the problem was you were programming. And the student kept talking about in terms of trains and stations. And I had to keep asking, what is a train? And he would look at me baffled, like, you know what a train is. It's the sequence of carriages that goes chug, chug, chug along a railway line. The point is, of course, that's not what you put into the program. In the program, you don't care what the way to the train is, depends what you're programming, but in the case of the timetable, you don't care, maybe where it was manufactured. There's lots and lots of irrelevant detail about a train and what a train is, which you don't care about in the program. What is relevant, of course, depends upon the problem you are formulating and trying to solve. But the important thing is you have to abstract away and keep only the relevant detail. In the terms that Aho and Ullman describes it, this means you construct an abstract data model and decide what actually gets represented in the data model away from the concrete, messy reality of the actual problem. Here's an example. Suppose you have a program which runs a taxi dispatching service. You have a set of available taxis, you have a set of waiting passengers, and you need to match them up. They might appear on your mobile phone with a little screen like this. So I already used the word sets. So we have a set of taxis and a set of passengers. Okay, and a set is sort of the simplest kind of data structure. It tells you that the only thing that matters is what the elements of the set are, and that's in some sense the only relationships. In practice, you will have a lot more detail, which will be relevant. You might want to minimize distance traveled by taxis and positions. You'll want responses in real time. You can't sort of wait for all taxis to become available and then do the matching and so on. But at the core, you have two sets of objects and you're trying to match them together. I'll give you another example which looks very similar. In practice, it's a completely different application, but there is a common core. Now, in the National Health Service here in England, they run a kidney matching program. What does this mean? So you have patients who need a kidney transplant, and very often they will have a relative who's willing to donate a kidney. But you have a willing donor and you have a patient in need of a transplant, but there may be tissues incompatibilities, which means you can't really donate the kidney to this particular patient. But sometimes you can find another donor-recipient pair and arrange a swap, right? So if donor 1 is compatible with patient 2 and donor 2 is compatible with patient 1, then you can arrange a swap. And this is sort of a common practice in the health service. In fact, that picture I've taken and showed you on the screen is taken from the actual kidney matching program as an illustration. Now, the chances of getting compatible pairs increases greatly if you have a bigger set of donors, a bigger set of recipients, and then you can set up a chain of compatible donors and so on. This illustration is also from the kidney matching program website. So once again here, you have two different sets, the set of donors and the set of recipients, and you're trying to match them up, just like in the taxi waiting example. So the way we say this is, at the core of both is there is a common algorithmic problem. Forget about taxis and passengers and kidneys and etc. What you have is two sets and a compatibility relationship across them. And this is what we call a bipartite graph, right? So bipartite graph, often depicted like this. So here we have two sets of 4 vertices, one on the left, one on the right. And a line between two vertices says that they are, in some sense, compatible. And we want to match them up, which means we want to find a perfect matching. A perfect matching is simply a subset of the edges in which each vertex is matched to exactly one other. Sorry, that one doesn't work because now we can't extend this. So what we can do is swap around and there we go. We have found a perfect matching. Thinking about the problem at this abstract level is what allows us to reuse algorithmic ideas. We can use the same essential algorithm for matching kidneys with patients as taxis with passengers. And in fact, this problem arises in many, many different situations. We're not always looking for a perfect matching, but maybe the largest possible matching we can find in a graph, and so on. Okay, I'm not talking just about being able to reuse code from one application to another, but more importantly, reusing the same fundamental insights. So to come up with an algorithm for finding a perfect matching requires a certain amount of insight. And formulating it abstractly allows us to formulate an insight which is then widely applicable. Okay, that's the essence of abstraction that I want to drive home. Now, in computer science, we often describe algorithms as Turing machines. And Turing machines is sort of one of the original abstractions in the subject. I'm sure you're all familiar with what a Turing machine is. Here's a very quick description. We think of it as a processor with finite memory and an infinite tape. And at any point, the processor can only look at one symbol on the tape. And based on its finite memory and the symbol it reads, it performs a transition, moves the tape head left or right, and changes its internal state. The Church-Turing thesis tells us that essentially all models of computation are equivalent to this one in terms of what they can and cannot compute. There's a strong version of thesis which says that up to polynomial time factors, they're all equivalent. But so the question arises, if essentially we have all models of computation are equivalent, why would we ever consider one other than this? And again, the key is abstraction. So you can perform any computation you like on a Turing machine, where the tape symbols contain just the tape contains just symbols, zeros and ones, like in this illustration. This involves coding all of your data as binary strings, which of course in practice is what happens in machines. But in some sense, you don't want to be thinking algorithmically at the level of bit strings. That's not the level at which you want to program. When you program, you want to think about your data more abstractly, right? So that's the reason why we bother with others. And in fact, the plethora of computation models, just think of the number of high-level programming languages out there, is because they give you different abstractions and therefore different ways of thinking about data, which underneath will be implemented as simple bit strings. But for the purpose of programming, you want to think of them more abstractly. There's a rich vein of theoretical research in theoretical computer science which looks at different abstractions and their formal semantic properties. Okay, we're not going to go down that route in this course so much. Just want to make one final point about Turing machines. We're not going to talk about Turing machines that much either. But the reason for we look at Turing machines is not because we want to program using Turing machines, but because they are very simple as a model of computation. And their simplicity is useful when we want to prove impossibility results. When you want to show something is undecidable, showing that you cannot do it on a Turing machine is enough. If you actually want to write a program to do something, you will choose a much richer language, knowing that ultimately they are equivalent. Now, when we think of algorithms, as I said, they're usually described by operations on abstract data, such as graphs. So for instance, we're thinking of an algorithm for matching kidney donors with patients. We think of it, we formulate it as a graph problem on bipartite graphs. And that's the way we think of the algorithm. But when we analyze algorithms, well, we might analyze an individual algorithm at that high level as well. But in the field of complexity theory, where we try and prove lower bounds, that is, we try and prove impossibility results for certain problems, we usually work with simple machine models like Turing machines precisely because impossibility results are easier. We expect, right? The simplicity of the machine is what allows that. And we think of them as operating on strings of symbols. We generally consider this to be a harmless mismatch because data structures can be encoded as strings. An arbitrary data structure can be encoded as a string. And so once you've shown that a Turing machine operating on strings can't solve a problem, let's say in polynomial time, then you know that no high-level program will be able to do it. But there is a cost to this. Translating data structures to strings breaks abstraction. And this is a point I wanted to make. Sometimes even high-level descriptions of algorithms break the level of abstraction, and I'm going to explore this a little bit. But when we try and analyze complexity at the level of abstraction at which we want to formulate the problem, for example, graph algorithms, it turns out there is a mismatch with ordinary complexity theory. And that mismatch is sort of the core of what we'll be studying in this course. Let's get back to the problem of graph matching, that is, finding a perfect matching in a bipartite graph. So we're given a bipartite graph which consists of two sets, A and B, of vertices, and E, an edge relation, which connects some edges and some vertices in A with vertices in B, right? Here's a very simple high-level description of an algorithm for finding a maximum size matching in such a graph. You start with an empty matching M. You choose a vertex in A which is currently unmatched, right? So there is no edge incident on A in our current matching M. And you find an augmenting path starting at A and ending in an unmatched B. I will tell you in a moment what an augmenting path is. And then you take the symmetric difference of this path P and the current matching M, and that is your new matching. And this is guaranteed to have one edge more than the previous matching. And when you can no longer do this, you know you have a maximum size matching. And it requires some proof that what you get is actually optimal, right, rather than just a local maximum. But in some sense, the fact that this gives you a maximum matching is a sort of significant proof in, well, if you will, in graph structure theory. So let me say a little bit more about augmenting paths. So the idea is the following. You have a vertex A currently unmatched. On the other side, so this means in particular that the various edges which are incident on A, none of them is part of the matching, right? So we can choose any one of them and look at the other endpoint, call it B. If B is also unmatched, then we can just add the edge AB to our matching and we've increased the size by 1. But if B is matched, let's say B currently has a neighbor that it's matched to. Let's call that one A1. And suppose that A1 has other edges incident on it. So, which will take us to some B1. Now, obviously, this edge that I've just drawn is not part of the matching, which means, of course, that either B1 is currently unmatched, in which case we stop. But if B1 is not currently unmatched, that means there's a matching edge. B1, which will take us to some A2. Okay? And we carry on this process until we hit a vertex in B, which is unmatched. Okay? Let's say B2 turns out to be unmatched. Okay, if we reach a vertex in B that's unmatched, the path which starts at A and goes there that we have just constructed is an alternating path using edges in the matching and edges which are not in the matching. And it contains exactly one edge more outside the matching than in the matching, because both endpoints are unmatched. And so if we flip, as this algorithm says, take the symmetric difference of M and P, right, of the path P and the current matching M, we increase the size of the matching by 1. Okay, and this algorithm is guaranteed to find you a maximum size matching. Okay, so it's sort of a greedy algorithm. Now, in the way I've described the algorithm, at each stage, right, we increase the size of the matching by 1, and then at the next stage, we choose an A currently unmatched. In fact, there are further choices we make, because not only do we choose A, for each A, there may be more than one unmatched edge we can follow. So we have to make choices. Okay. How do we make these choices? Now, in a typical implementation, you will have the graph represented as some sequence of lists, and you'll simply take the next vertex in the list. When you do that, you're breaking the abstraction, in the sense that as far as the graph is concerned, all vertices are the same. To use the ordering in a list in order to treat them differently is what I call you're relying on concrete hidden data rather than in the just the abstract form of the data structure, which is the graph. The way this gets expressed, the way we think about it, is that abstract data has symmetries. that an abstract algorithm should respect. Okay, if we expect an algorithm, for instance, to work at the level of abstraction of graphs, then it must respect the symmetries of the graph. If we have a pair of nodes in the graph which are indistinguishable by properties of the graph itself, then they should not be distinguished in any way by the algorithm. This is, in some sense, the slogan of symmetry in algorithms that we'll adopt. It raises an interesting question. What algorithms have this property of respecting symmetry? Okay. How severe a restriction is this on our ability to write algorithms? Because I just gave you an example of a natural graph matching algorithm which is not symmetric in this sense. That's a sort of key part of what we'll be exploring. Before I move on to looking at some examples of how these symmetries arise, I thought I'd say a little bit specifically about the matching problem, because the matching problem is going to be another recurring theme, a recurring example in our course of lectures. The algorithm that I just outlined for finding a maximum size matching in a bipartite graph, this is quite old. It goes back to Ford Fulkerson and their work on the max flow problem in graphs. And it goes back to the 1950s, I suppose. It's interesting also that Edmonds was exploring algorithms for matching abstractly in terms of, for example, linear programming and their representation as polytopes. And it was in this context that he formulated what he called good algorithms, which is really algorithms that run in polynomial time. And this is in some sense regarded as the beginnings of the study of complexity theory, right? Where polynomial time was first identified as a feature one looks for in an algorithm. The other sort of key landmark in the beginnings of complexity theory, I suppose, is the definition of NP completeness, which came with the work of Cook and Levine in the early 70s. The fastest algorithm we know for finding a perfect matching in a graph, not just a bipartite graph, more general, is the one by Micali and Vazirani. And it runs in time roughly, big O of square root of the number of vertices times the number of edges. It's interesting that if you look at the Micali and Vazirani algorithm, it is not symmetric. I'll say more about that in a minute. So it's an interesting question which I want to pose to you. By the end of the course, we will see an answer to this. But can you solve the perfect matching problem by an efficient and symmetry respecting algorithm? Okay. So what do I mean by efficient? So efficient means, can you do it in polynomial time, but respecting symmetry? In some sense, it's easy to come up with a symmetry respecting algorithm by just sort of parallelizing the algorithm I showed you, any one of these. Whenever you have to make a choice, just take all possible choices, right? And try them, whether if you want to do it sequentially, one by one, or in parallel. The point is you get a symmetry respecting algorithm, but it might be exponential size. It might take exponential time. So satisfying both the requirements of efficiency and symmetry is what this question is about. And as I already alluded to, the Micali-Vazirani algorithm does not give you such symmetry preserving efficient algorithm. And it's interesting. After the 1980 paper by Micali and Vazirani, considered a major breakthrough in algorithmic graph theory, Vazirani published a follow-up paper, nearly 70 pages, in which he proved the correctness of the algorithm they had described. And it's a very complicated proof which tries to show inductively that the data structures that the graph constructs satisfy certain properties which guarantee that you eventually find the maximum size matching in a graph. And in describing these data structures, at a certain point, Vazirani talks of I mean, he defines a lot of graph structure theory and data structures, and then he defines something he calls an anomaly, and very specifically points out that this is a feature of the algorithm and cannot be described purely in terms of the structure of the graph. And if you look at that carefully, what that means really is that this is a feature of the data structure which is not preserved by the symmetries of the graph, and is sort of extraneously imposed by the algorithm. And that's in some sense pinpoints the place where the algorithm breaks symmetry. So where does symmetry arise? I mean, what's wrong with just having an algorithm which breaks symmetries like the Mikhali-Vazirani algorithm does? Well, symmetry arises very often when you describe your problems at high level and use them to automatically generate algorithms from high-level descriptions, because the high-level descriptions are described at the level of the abstract data structure. Here's an example. Here's a specification, say, of a relation M in a graph. M is a set of pairs, and this is what it says, that M is a perfect matching, right? It says for every pair of vertices x, y, if they're in the relation M, then there's an edge from x to y, right? So M is a subset of the edge relation. And for every vertex, there's a unique y for which x, y is in the relation, right? So any relation which satisfies this condition is a perfect matching. And what we might think of is, this is a specification for M, and we want to generate from such a specification automatically an algorithm for finding an M if such a one exists, or verifying whether such an M exists. The point is that almost any general purpose way you think of turning such a specification into an algorithm will most likely be exponential, because it will search for all possible sets M to see whether you can find one that satisfies this. Okay. I'm now going to move on to looking at some specific examples where such algorithms generated from high-level specifications have been looked at, and the question of symmetry has arisen in several different contexts in the field of theoretical computer science. So we'll run through a few of these after a brief pause.